46 years ago, two spacecraft left Earth carrying a message to aliens. Voyager One and Voyager Two now travel through a region no human-made object has ever explored. They fly through interstellar space at 38,000 miles per hour. Each probe carries instruments designed in the 1970s, powered by plutonium batteries slowly dying in the cosmic dark. In 2012, Voyager One crossed the heliopause, the edge where our sun's influence ends. Scientists expected silence. Instead, the probe detected something strange, a persistent hum vibrating through the void between stars. Plasma waves rippling through interstellar space at frequencies never before measured. The fabric of space itself resonates with energy we did not know existed. Voyager 2 confirmed the readings when it crossed over in 2018. Both spacecraft hear the same cosmic drone, a sound that fills the galaxy but reaches Earth as silence. The data reveals that interstellar space is not empty. It pulses with charged particles, magnetic fields twisted into configurations our models cannot explain, and waves that suggest the galaxy is far more active than we believed. If you find this fascinating, hit that like button and subscribe. We begin now. The Voyagers launched in 1977 with 8-track tape recorders, the same technology people were using to listen to Fleetwood Mac on road trips. The same technology that would be completely obsolete within 5 years. The spacecraft that would travel farther than anything humans ever built runs on tech that was already dying when it left the ground. Think about what that means. These machines were designed with slide rules and hand calculations. Pocket calculators were not common yet. Engineers worked through orbital mechanics problems by hand, checking their work with tools that would look primitive in a modern high school. They ordered parts from Radio Shack catalogs, the same catalogs you could flip through at the mall. The Voyager spacecraft store less data than a single photo on your phone, 536 megabits total. Everything they have learned about 4 planets, their moons, the edge of our solar system. It would fit on a 1990s floppy disk with room to spare. The computers have 69.63 kilobytes of memory. Your car key fob has more computing power than Voyager. The spacecraft that discovered volcanoes on Io and crossed into interstellar space runs on less memory than it takes to open this video. I think about this sometimes. We cannot keep a laptop running for 5 years without it becoming unbearably slow. And yet, every piece of technology in your house right now will be in a landfill long before Voyager stops moving. Your phone, your laptop, your TV, the iPhone you threw away in 2010 is already extinct. Voyager is still calling home. The 8-track player in Voyager has been recording and playing back data for 47 years. Every 8-track player on Earth is in a museum or a landfill, but somewhere past the edge of the sun's influence, where no sunlight reaches, where the solar wind becomes a memory, a tape is still turning, still recording, still rewinding, still working. You threw away 3 phones in the time it took Voyager to reach the heliopause. The data transmission rate is 160 bits per second. That is slower than the slowest dial-up modem you remember, slower than the connection that made you wait 5 minutes for a single image to load, line by line, back when the internet was new. Voyager sends back data at a speed that would be unusable today for literally anything. You could not load a text-only website at 160 bits per second. But the spacecraft does not need to load websites. It needs to send back measurements of plasma density, magnetic field strength, cosmic ray counts. Numbers, simple data points that describe what exists in a place no human will ever visit. And for that, 160 bits per second is enough. The Voyagers were built with technology already obsolete by the time they reached Jupiter. The 8-track tape recorder they used was discontinued for consumer use in 1982, 3 years after Voyager 1's Jupiter encounter. These spacecraft are proof that obsolete does not mean useless. It just means we stopped paying attention. Consider what we mean when we say something is obsolete. We mean it cannot do what we currently want. It cannot run the latest software, display the newest formats, connect to modern networks. Obsolete means incompatible with now. But Voyager does not exist in now. It exists in the gap between stars, where now is a meaningless concept. Light from Earth takes 22 hours to reach Voyager One. 22 hours. When engineers send a command, they wait almost 2 days for confirmation. The spacecraft operates in a time frame where our idea of relevance simply does not apply. The technology works because it was built for a specific purpose, not to be upgradable, not to be versatile, not to last forever, just to keep functioning long enough to do one thing: send back data from places we cannot go. It has been 47 years. The Voyagers are still doing that one thing. The engineers who built these machines are retired now. Some have passed away. The technology they used to design the spacecraft is in museums. The companies that manufactured the parts have been bought and sold and dissolved. The world that created Voyager is gone. The spacecraft remain. They keep transmitting. They keep measuring. They keep moving through a darkness that has no reference point for what obsolete means. Your laptop will not make it 5 years. Your phone starts slowing down after 2. The car in your driveway will need replacement parts within a decade. Everything we build now is designed with planned obsolescence built in. We expect things to fail. We design them to be replaced. The Voyagers were not designed that way. They were designed by people who knew this would be their only chance. One launch window, one alignment of planets that happens once every 176 years. If the spacecraft failed, there would be no second attempt. Not in any of our lifetimes. That knowledge shaped every decision. Every component was tested beyond normal limits. Every system had backups. Every circuit was built to handle radiation, temperature extremes, and the vacuum of space for longer than anyone thought possible. The result is machines that should not work, that have outlived every prediction, that continue to function in an environment hostile to everything we know how to build. With technology we consider laughably primitive, they are still out there, still recording data on tape systems from the 1970s, still computing with memory measured in kilobytes, still transmitting at speeds slower than your first modem, still working. And they are about to show us something that all our modern technology, all our advanced computers, all our sophisticated instruments have never seen. Voyager One is now 24 billion kilometers from Earth. Let's make that number mean something. If you started walking the day the Great Pyramid was completed, never stopped, never slept, never died, just walking at normal human pace for 4,500 years, you still wouldn't be halfway to where Voyager is now. You'd have walked through the entire span of recorded human civilization, every empire that rose and fell, every war, every discovery, every generation, and you wouldn't be halfway there. Voyager 2 trails behind at 20 billion kilometers. That's 134 astronomical units. An astronomical unit is the distance from Earth to the Sun. Voyager 2 is 134 times farther from the Sun than we are. It has crossed that distance 134 times over. The warmth you feel on your face from sunlight, Voyager feels almost nothing, just the faint whisper of a star that's barely brighter than the others. If you got in a car when the Roman Empire fell in 476 AD and drove at highway speed, never stopping for 1,548 years, you'd arrive at Voyager 1's position just in time to watch the sun expand into a red giant and swallow the Earth. You'd have driven through the entire medieval period, the Renaissance, the Industrial Revolution, both world wars, the space age itself, and you'd just barely arrive. You'd arrive at the exact moment when everything you left behind ceases to exist. The spacecraft are traveling at 61,000 kilometers per hour. That's 17 kilometers every second, fast enough to cross the United States in 4 minutes, fast enough to circle the Earth at the equator in just over 2 hours. They have been traveling at this speed for 47 years. They have never stopped, never slowed down, never rested. 47 years of constant motion through absolute darkness. Every year, Voyager 1 moves 1.5 billion kilometers farther away. That's the distance from the Sun to Saturn. Every single year, the gap between us and the spacecraft grows by an entire planetary orbit annually. By the time you watch this video, Voyager will be millions of kilometers farther than when the script was written. By next year, another 1.5 billion. The distance just keeps accumulating. Light takes 22 hours to reach Voyager 1 from Earth. 22 hours. Light, the fastest thing in the universe, traveling at 300,000 kilometers per second, needs nearly a full day to get there. When engineers send a command to Voyager, they send it and then go home, sleep, come back the next day, and the signal is still traveling. It's a 22-hour conversation delay one way, 44 hours round trip. You could watch an entire season of a TV show in the time it takes to say hello and hear a response. Think about what that means for operating the spacecraft. Every decision has to account for this delay. If something goes wrong, the spacecraft has to handle it alone. There's no real-time control, no joystick, no immediate correction. The commands are sent with the knowledge that by the time they arrive, the situation may have already changed. Voyager operates in a state of permanent isolation. It receives instructions from a world it left behind 2 decades ago in travel time. Here's something most people don't realize. Voyager 1 is the most distant human-made object. That part you probably know. But it's not moving away from us in a straight line anymore, because the Sun itself orbits the galactic center at 800,000 kilometers per hour, and because Earth orbits the Sun at 107,000 kilometers per hour. The actual path Voyager traces through the galaxy is a spiral, a corkscrew. It's not heading away in some pure straight trajectory into the cosmic void. It's spiraling outward while we all spin through space together. We're not watching it leave. We're watching it spiral away while everything moves. The Sun, the Earth, Voyager, all of us tracing curves through the galaxy. All of us in motion together, even as the distance between us grows. The spacecraft adds another 400 million kilometers to that spiral every month. That's roughly the distance from the Sun to the asteroid belt. Every month. Another astronomical unit every 16 months. The numbers stop feeling real after a while. 20 billion kilometers. 24 billion kilometers. The human brain didn't evolve to grasp distances like this. We evolved to judge the distance to the next tree, the next water source, the next shelter, not the edge of the solar system. So we used time instead. 47 years of travel, 47 years since launch. That's easier to hold. A person born the day Voyager launched is now middle-aged, has lived an entire life, childhood, adolescence, career, maybe children of their own, and Voyager has been traveling that entire time, moving, recording, transmitting, never stopping. While generations have grown up, the spacecraft just keeps going, farther than anything we've ever built, farther than anything we've ever touched, still working, still sending data back across a gap that takes light nearly a full day to cross, still out there, still moving, still spiraling outward into the dark. The planets aligned in the late 1970s. Jupiter, Saturn, Uranus, Neptune, all of them arranged in a sweeping arc across one side of the solar system, like pearls on a cosmic string. This alignment happens once every 176 years. Think about that frequency. The planetary alignment happens as often as your family has a reunion where every single person shows up, including the relatives who moved to different continents, the ones who stopped talking to each other, and the ones who've been dead for 50 years. It almost never happens. The last time it occurred, the United States didn't exist. Thomas Jefferson wasn't born. Beethoven wasn't born. The Declaration of Independence was still 90 years away. And the next time it happens, everyone reading this will be gone. Your children will be gone. Your grandchildren will be old. The window opens in the 2150s. Gary Flandreau figured out what this meant in 1965. He was a young engineer at the Jet Propulsion Laboratory. His job was to calculate possible trajectories for future missions to the outer planets. He was playing with orbital mechanics, running numbers, and he noticed something. The planets were going to line up, not perfectly, but close enough. And if you launched at exactly the right moment, you could use them, all of them, one after another. The concept is called gravity assist, sometimes called a gravitational slingshot. The idea is simple. The execution is anything but. A spacecraft approaches a planet. The planet's gravity pulls it in, but the spacecraft isn't trying to orbit. It's trying to pass by at just the right angle, just the right speed. As it swings around the planet, it steals a tiny fraction of that planet's orbital momentum. The planet is moving. The spacecraft is moving. They interact, and when the spacecraft leaves, it's moving faster than when it arrived. The planet slows down by an infinitesimal amount. So small, it's unmeasurable. The spacecraft speeds up by thousands of kilometers per hour. Picture playing pool on a table the size of a solar system. The balls are planets moving at different speeds, and you have to sink a shot that bounces off 4 moving balls over the course of 12 years. You get one shot. If you miss, everyone alive today will be dead before you get another chance. Voyager made the shot. The math Flandreau calculated was staggering. Without gravity assists, a spacecraft heading to Neptune would take about 30 years. 30 years of travel time using conventional propulsion and a direct trajectory. That's 30 years of keeping a spacecraft operational in the radiation and cold of deep space. 30 years of aging electronics. 30 years of potential failures. But with the alignment, with gravity assists at each planet, you could do it in 12 years, less than half the time, and you'd visit all 4 outer planets along the way: Jupiter, Saturn, Uranus, Neptune, a grand tour of the solar system's giants. NASA called it exactly that, the Grand Tour. The mission plan was ambitious. 2 spacecraft, maybe more, launched in the late 1970s, equipped with enough instruments to study each planet in detail, enough power to last through the entire journey, enough redundancy to survive 12 years in space. The cost estimate came back high, very high, too high. NASA rejected it. Not enough budget, not enough political support. The Grand Tour was shelved. Instead, they approved something smaller. 2 spacecraft called Voyager, Voyager One and Voyager Two. The mission parameters were limited. Visit Jupiter, visit Saturn. That's it. No Uranus, no Neptune, no Grand Tour. Just the 2 largest planets and then coast into the dark. The budget was a fraction of what the Grand Tour would have cost. The mission timeline was shorter. The objectives were narrower. It was the mission NASA could afford, not the mission the engineers wanted. This is the part that gets me. The engineers built the spacecraft anyway, not the limited version, the full version. They designed Voyager to survive the complete Grand Tour, even though they weren't funded for it. Even though the official mission only included Jupiter and Saturn, they added redundancy. They added shielding. They added trajectory options. They built the spacecraft to last 12 years, not 4. They built it to handle the radiation environment at Uranus and Neptune. They built it for the mission they wanted, not the mission they were approved for. It was an act of rebellion, quiet, professional, but rebellion nonetheless. They bet that if Voyager One and Voyager Two successfully completed the Jupiter and Saturn encounters, NASA would extend the mission. They bet that the data would be too good to pass up. They bet that the opportunity was too rare to waste. And they were right. Voyager 2 launched on August 20th, 1977. Voyager 1 launched 16 days later on September 5th. The launch window was narrow, a few weeks in the summer of 77. Launch earlier and the planets wouldn't be in position yet. Launch later and you'd miss the alignment entirely. The next chance wouldn't come until 2154, 177 years later. The trajectory was absurdly precise. At Jupiter, Voyager 2 had to pass within a few 100,000 kilometers of a specific point, not just anywhere near Jupiter, a specific point in space at a specific time. Miss by too much, and the gravity assist wouldn't work. The spacecraft would be deflected onto the wrong trajectory. It wouldn't reach Saturn at the right angle. The entire mission would unravel. The same precision was required at every planet. Every encounter had to work perfectly, or the next one wouldn't happen at all. Imagine that pool shot again. You're not just hitting one ball. You're setting up a chain reaction that takes over a decade to complete. Each ball has to deflect the cue ball at exactly the right angle. Too steep and you miss the next ball entirely. Too shallow and you don't gain enough speed. And you can't adjust mid-shot. Once you strike, physics takes over. The balls move. You watch. And you hope the math was right. The math was right. Voyager 1 reached Jupiter in March of 1979. Voyager 2 arrived in July. Both gravity assists worked. Both spacecraft accelerated towards Saturn. Voyager 1 arrived at Saturn in November of 1980. Voyager 2 in August of 81. The primary mission was complete. Jupiter and Saturn. Data beyond anything scientists had hoped for. Both spacecraft were still functioning, still healthy, still transmitting. NASA approved the extension. Voyager 2 would continue to Uranus, then Neptune. The mission the engineers had quietly prepared for was now official. The Grand Tour was happening after all, just with one spacecraft instead of two. Voyager 1 had used its Saturn encounter to fly past Titan, Saturn's largest moon. That trajectory sent it out of the plane of the solar system, up and away from the remaining planets. It wouldn't visit Uranus or Neptune, but it would become the first human-made object to leave the solar system entirely. A different kind of grand tour. Voyager 2 had 12 years of travel ahead. Uranus in 86, Neptune in 89. Then the slow coast into interstellar space. The rarest opportunity in human history was unfolding. A mission that couldn't happen again for over a century. A mission that almost didn't happen at all. And it was working. The revelations began at Jupiter. Voyager 1 arrived in March of 1979. Voyager 2 followed in July. The mission had been designed around these encounters. Everything depended on what the spacecraft would find. What they found changed planetary science forever. Voyager 1's cameras turned toward Io, one of Jupiter's largest moons. Scientists expected a dead, cratered surface. They'd been looking at Io through telescopes for 400 years. There was no reason to think it was special. Then the images came back. The surface was yellow and orange and red. No craters. None. Just smooth plains interrupted by dark spots. Navigation engineer Linda Morabito noticed something strange in one of the images. A crescent shape extending beyond the moon's edge. She ran the calculations. It wasn't an artifact. It wasn't a glitch. It was a plume. Volcanic material shooting 300 kilometers into space. Imagine looking at the moon and seeing it explode. Not metaphorically, literally seeing plumes of sulfur shooting 300 kilometers into space. That's what Voyager saw at Io. We'd been looking at Jupiter's moons through telescopes for 400 years. It took 400 years to realize one of them was turning itself inside out. The discovery violated everything we thought we knew about volcanism. Before Voyager, we thought volcanic activity required a planet the size of Earth or larger. Io is smaller than our moon. It's the most volcanically active body in the solar system, and it shouldn't be. Its core should have frozen solid billions of years ago. Something was keeping it molten. Something was generating enough heat to power constant eruptions. The answer was Jupiter itself. Jupiter's gravity squeezes Io like a stress ball, over and over. As Io orbits, the gravity pulls harder on one side than the other. The moon flexes, stretches, compresses. That flexing generates heat, enormous amounts of heat, enough to keep the interior molten, enough to turn the entire moon into a volcanic engine. Io is volcanic because Jupiter won't stop squeezing. Its tidal forces as torture, repeated for 4 billion years. The spacecraft moved on to Europa, another of Jupiter's large moons. The surface looked strange, bright, almost white, covered in cracks and lines. Europa's surface looks like someone dropped a porcelain ball and glued it back together. Every crack, every line, they're not random. They're the surface of an ocean, frozen and refrozen and cracked by tides from Jupiter's gravity. There's more liquid water under Europa's ice than in all of Earth's oceans. We found an ocean on a moon before we'd finished mapping our own. The implications hit immediately. Liquid water, warmth from tidal heating, organic chemistry delivered by comets. Europa had the ingredients for life, not just the possibility. The ingredients, right there, orbiting Jupiter, hidden under kilometers of ice. The discovery shifted the entire framework of astrobiology. Life didn't require an Earth-like planet. It just required liquid water and an energy source. Europa had both. Voyager also found Jupiter's ring system. faint, dusty, nothing like Saturn's brilliant rings, but rings nonetheless. No one had predicted them. The Great Red Spot revealed itself as an enormous storm system, larger than Earth, with wind speeds exceeding 400 kilometers per hour. That's faster than the strongest tornadoes ever recorded on Earth, and it had been raging for at least 300 years, maybe longer. Both spacecraft left Jupiter and headed for Saturn. Voyager One arrived in November of 1980, Voyager Two in August of 1981. The ring system dominated the view. From Earth, Saturn's rings looked smooth, continuous bands of material circling the planet. Voyager showed the truth. The rings weren't smooth. They were made of thousands of individual ringlets, narrow bands separated by gaps. Each ringlet had sharp edges, precise boundaries. The structure was far more complex than anyone had imagined. The question was why? Why didn't the rings blur together? Why didn't they spread out over billions of years? The answer came from tiny moons embedded in the ring system. Moons no bigger than a city block. Their gravity nudged ring particles back into line, kept the edges sharp, prevented the rings from drifting apart. Saturn's rings should have drifted apart billions of years ago. They're held in place by tiny moons, some no bigger than a city block, whose gravity acts like a sheepdog keeping the ring particles in line. Moons herding rings. Gravity as a shepherd. Voyager 1 made a close pass of Titan, Saturn's largest moon. Titan was shrouded in haze. The cameras couldn't see the surface, but the instruments detected something unexpected. An atmosphere, thick, dense, made mostly of nitrogen, just like Earth's atmosphere. Titan's atmosphere is actually thicker than ours. The surface pressure is 1.5 times what you experience standing at sea level. Titan became the only moon in the solar system known to have a substantial atmosphere, the only world besides Earth with stable liquid on its surface. Not water, methane and ethane, lakes and seas of hydrocarbons, hidden beneath the orange haze. Voyager 2 sent back images of Saturn's North Pole. The storm there didn't look like storms on Earth or Jupiter. It was hexagonal, 6 sides, perfectly geometric, each side longer than the diameter of Earth, a hexagonal storm. The shape is created by jet streams flowing at different speeds, creating standing wave patterns. But seeing it was surreal. Nature doesn't usually make hexagons. Saturn did. The encounters at Jupiter and Saturn weren't just successful. They were revolutionary. Volcanism on a moon smaller than ours. Oceans hidden under ice. Ring systems shepherded by gravity. Atmospheres on moons. Hexagonal storms. Every assumption had been challenged. Every prediction exceeded. The spacecraft had traveled billions of kilometers, used gravity from Section 4's carefully planned assists to reach these worlds, and revealed them as far stranger and more dynamic than anyone had imagined. These weren't just points of light in telescopes anymore. They were worlds, complex, active, full of processes we were only beginning to understand. And Voyager 2 still had 2 more planets ahead. After Saturn, the Voyagers separated for the last time. Voyager 1 turned upward, away from the plane of the solar system, beginning its climb toward interstellar space. The mission planners had made a choice at Saturn. They could send Voyager 1 close to Titan, Saturn's largest moon, or they could aim it toward Uranus and Neptune. They chose Titan. That trajectory meant Voyager 1 would be flung upward and outward, leaving the planets behind forever. Voyager 2 continued alone. For 5 years, it traveled through empty space to reach Uranus. 5 years, no planetary encounters, no course corrections using planetary gravity, just traveling, alone, through the dark, hoping the trajectory calculated a decade earlier was correct. The spacecraft was crossing distances where a single miscalculation, one tiny error in angle or velocity from the Saturn flyby, would mean missing Uranus entirely. There would be no second chance, no way to turn around. The fuel budget allowed for minor adjustments, but if the trajectory was significantly wrong, the mission would simply continue into the void, never encountering another world. It was correct. In January of 1986, Voyager 2 reached Uranus. The encounter revealed a planet tilted on its side, rotating like a rolling ball rather than a spinning top. But the real shock came from the magnetic field. Imagine if Earth's magnetic north was where Central America is. and the field wobbled like a drunk compass as the planet rotated. That's Uranus. Its magnetic field doesn't align with its rotation, doesn't center on the planet's core. It's offset and tilted as if the planet's insides don't match its outside. The field is tilted 59 degrees from the rotation axis, offset from the center by 1/3 of the planet's radius. Every scientist studying the data assumed there had been an equipment malfunction. There hadn't been. We still don't know why. The prevailing theory before Voyager 2 was that planetary magnetic fields aligned with rotation. Earth's does. Jupiter's does. Saturn's does, mostly. Uranus broke the model. The magnetic field is generated deep inside the planet, in layers of compressed water and ammonia that conduct electricity under extreme pressure. But something about the internal structure, some asymmetry we can't see or measure from Earth, creates this bizarre tilted offset field. The field rotates with the planet, so it wobbles wildly as Uranus spins, creating a magnetosphere that flaps and twists like a windsock in a hurricane. 3.5 years later, in August of 1989, Voyager 2 reached Neptune, 30 times farther from the Sun than Earth. It receives 1/900th the sunlight. A drive from Earth to Neptune at highway speed would take 5,000 years. 5,000 years of nothing but forward motion, and you'd finally arrive at a world so distant, the Sun looks like just another bright star. Neptune should have been dead, frozen, quiet. It wasn't. Neptune is 30 times farther from the Sun than Earth. It receives 1/900th the sunlight. It should be a frozen, dead world with barely a breeze. Instead, it has the fastest winds in the solar system, 3 times faster than a commercial jet at cruise altitude. Wind speeds measured at 2,400 kilometers per hour. That's 2,400 kilometers per hour. Winds moving at 667 meters per second. Something is generating enormous energy inside Neptune, and we don't know what. The planet radiates more than twice as much heat as it receives from the Sun. Some internal engine, some process left over from the planet's formation 4.5 billion years ago, is still running, still pumping energy into the atmosphere, creating storms and jet streams on a world that should be meteorologically inert. Voyager 2 photographed the Great Dark Spot, a storm system the size of Earth, spinning counterclockwise in Neptune's southern hemisphere. The images showed white clouds riding along the storm's edge, methane ice crystals condensed at high altitude where temperatures drop low enough for methane to freeze. The spot looked like Jupiter's Great Red Spot, a massive anticyclonic storm. Scientists expected it to be permanent, another ancient feature of a gas giant. When the Hubble Space Telescope observed Neptune 5 years later, the Great Dark Spot was gone, just gone. Storms on Neptune form and disappear on timescales we're still trying to understand. The magnetic field at Neptune matched Uranus, tilted 47 degrees from the rotation axis, offset from the center by more than half the planet's radius. 2 planets, 2 wildly misaligned magnetic fields. This wasn't a fluke. This was telling us something about ice giants, about how their interiors differ from gas giants like Jupiter and Saturn. We just don't know what that something is yet. The real surprise came from Triton. Triton is Neptune's largest moon. Voyager 2 passed within 3,900 kilometers of its surface, close enough to see details smaller than a kilometer across. The surface temperature measured -235 degrees Celsius, cold enough that nitrogen freezes solid, cold enough that most materials become brittle as glass. Voyager 2 found geysers, active nitrogen geysers erupting from beneath Triton's icy crust, shooting plumes 8 kilometers high. At -235 degrees, this moon is geologically active. Something is heating Triton's interior. Tidal forces from Neptune, or residual heat from its formation, or both. We don't know, but we saw the geysers, dark streaks across Triton's surface where nitrogen and dark organic material had been vented from below and deposited by winds in the thin atmosphere. Then there's Triton's orbit. Triton orbits backward. Every other major moon in the solar system orbits in the same direction as its planet's rotation. Not Triton. It orbits retrograde, clockwise, while Neptune spins counterclockwise. This means Triton wasn't born around Neptune. It was captured, gravitationally kidnapped from somewhere else in the outer solar system, probably a Kuiper Belt object, a dwarf planet wandering too close to Neptune billions of years ago. Neptune's gravity grabbed it, and Triton has been orbiting ever since. But because its orbit is backward, Neptune's gravity is slowly pulling it inward. The tidal forces that heat Triton's interior are also dragging it closer to Neptune, centimeter by centimeter each year. In a few 100 million years, Triton will cross the Roche limit and be torn apart, giving Neptune a ring system that will rival Saturn's. We're seeing a moon in its final orbit before execution. Voyager 2's encounter with Neptune ended on August 25, 1989, 12 years after launch. The spacecraft had visited all 4 gas giants: Jupiter, Saturn, Uranus, Neptune, 48 moons, thousands of images, magnetic field measurements, atmospheric data, discoveries that rewrote planetary science. After Neptune, the trajectory carried Voyager 2 downward and outward, away from the plane of the solar system, heading in the opposite direction from Voyager 1. Both spacecraft were leaving the planets behind, both aimed for interstellar space, but they would cross that boundary in different directions, sampling different parts of the heliosphere's edge. These encounters at Uranus and Neptune are the only close-up views humanity has of the ice giants, the only detailed measurements of their magnetic fields, atmospheres, ring systems, and moons. No mission has returned since. None is planned for decades. Voyager 2 flew by these worlds once, for a few hours each, and that data is all we have. Think about that. Everything we know about Uranus and Neptune in detail comes from a single spacecraft pass over 30 years ago. The images of Triton's geysers, the measurements of Neptune's winds, the discovery of Uranus's tilted magnetic field, all from Voyager 2, all from encounters that lasted less than a day each. The spacecraft kept transmitting as it left Neptune behind, still functional, still sending data, still powered by the same source that had kept it alive for 12 years across billions of kilometers. That power source would determine how long the mission could continue, how far into interstellar space Voyager could travel before going silent forever. That power source is a radioisotope thermoelectric generator, an RTG, 3 of them, actually, mounted on a boom extending from Voyager's body. Each one is a simple device, no moving parts, no combustion, no chemistry, just heat, converted directly into electricity. Here's how they work. Inside each RTG sits a pellet of plutonium, 238. The plutonium decays. Atom by atom, it breaks down into lighter elements, releasing heat. That heat radiates outward to thermocouples, metal junctions that convert temperature differences into electrical current. The hot side faces the plutonium. The cold side faces space. The temperature difference generates power. At launch, Voyager's 3 RTGs produced 470 watts combined. That's about what 5 old incandescent light bulbs would draw. Enough to run the cameras, the instruments, the computers, the radio transmitter. Enough to keep Voyager alive. The plutonium inside Voyager is dying. Not suddenly, slowly, atom by atom, over decades. When Voyager launched, the plutonium was hot enough to power all the instruments, cameras, transmitters, computers. Each year, a little cooler. Picture an ember from a campfire that never goes out, but slowly, steadily dims. By the 2030s, it will be too cool to power even the most basic instruments. The ember will still be glowing. It'll glow for centuries, but it won't be enough to keep the transmitter alive. Plutonium-238 has a half-life of 87.7 years. That means every 87.7 years, half of the plutonium atoms will have decayed. Half the heat, half the power. Voyager launched in 1977. We're not even halfway through the first half-life yet, but the power loss doesn't wait for the math to catch up. Voyager 1 currently generates about 249 watts. That's down from 470 at launch. The spacecraft loses about 4 watts per year. 4 watts doesn't sound like much. It's less than a nightlight. But when you only have 249 watts to work with, every watt matters. The power loss isn't just from plutonium decay. The thermocouples degrade too. RTGs don't fail suddenly. They degrade. The thermocouples that convert heat to electricity become less efficient over time. It's not that the plutonium stops producing heat. It's that the conversion process slowly breaks down. Imagine a translator who gets more tired each year, losing words, until one day they can't translate at all, even though they still understand both languages. Why not use solar panels? Every spacecraft near Earth uses them. They're lighter, they're simpler, they don't require plutonium. The answer is distance. At Jupiter, sunlight is 25 times weaker than at Earth. At Neptune, it's 900 times weaker. A solar panel that could power Voyager at Earth would need to be the size of a tennis court at Jupiter. At Neptune, the size of a football field. And that's before accounting for degradation, dust, and the fact that solar panels add weight. Engineers calculated that solar panels at Jupiter would generate 0.07% of the power Voyager needed. 0.07%. Essentially nothing. RTGs were the only option. There was never a choice. The outer solar system is dark. Past Mars, sunlight becomes a suggestion rather than a resource. Voyager needed a power source that didn't care about the sun, that didn't depend on light or proximity or seasons. RTGs provided that. Steady, reliable, independent. They've been running for over 46 years without pause. No maintenance, no refueling, just the slow, predictable decline of radioactive decay. The plutonium-238 inside Voyager's RTGs is extraordinarily rare. It doesn't occur naturally in meaningful quantities anywhere on Earth. You can't mine it. You can't extract it from ore. It only exists because of nuclear reactors. We make it by irradiating neptunium-237 in a reactor, then chemically separating the plutonium-238 that forms. It's a manufactured element, rarer than gold in practical terms. At the time of Voyager's launch, the United States had a stockpile. Then we stopped producing it. For decades, we didn't make any more. The infrastructure shut down. The expertise scattered. NASA had to buy plutonium-238 from Russia to power later missions like Cassini and New Horizons. We only restarted domestic production in 2015. The power source keeping Voyager alive is rarer than gold, manufactured in nuclear reactors, and we almost lost the ability to make it entirely. Think about that. The spacecraft traveling farthest from Earth, carrying humanity's message to the stars, is powered by a substance we briefly forgot how to produce. Every year, mission engineers calculate how much power remains. They decide which instruments to turn off, which heaters to disable, which systems can survive a little colder. The mission is a slow process of triage. What can we lose and still call this a success? What must we keep running at all costs? The radio transmitter is non-negotiable. Without it, Voyager becomes a silent tomb. The attitude control system is essential. Without it, the antenna drifts away from Earth and the transmitter becomes useless anyway. The plasma wave instrument, the magnetometer, these are the last priorities. The final voices. By the early 2030s, maybe 2036 if we're lucky, the power will drop below the minimum threshold. The transmitter will shut down, not because it's broken, not because the plutonium stopped decaying, just because there isn't enough electricity to keep the signal alive. The RTGs will continue generating heat for centuries. The plutonium will keep decaying, oblivious to whether anyone is listening. The thermocouples will keep converting heat to electricity, even as that electricity powers nothing. Voyager will drift through interstellar space, warm at its core, eternally generating a few watts of power with no instruments left to use it. The ember still glowing, but the fire, for all practical purposes, gone. This power constraint shapes everything. How Voyager orients itself, how it communicates, how mission controllers sequence commands to minimize energy use. Every decision traces back to those 3 RTGs and their slow, irreversible decline. The power source that was supposed to last a decade has lasted nearly 5. But even that triumph is temporary. The countdown continues. The watts slip away, and eventually, silence. The power limitation from those decaying RTGs creates another challenge, one that sounds simple but becomes almost impossible at interstellar distances. Voyager has to stay pointed at Earth, not approximately pointed, not roughly aimed in the right direction, pointed within 1/10 of 1 degree. That precision matters because Voyager's high-gain antenna is directional. It doesn't broadcast in all directions like a light bulb. It focuses its signal into a narrow beam, concentrating every precious watt toward one tiny blue dot 22.5 billion kilometers away. Miss that target by even a fraction of a degree, and the signal scatters into space. All that data, all those measurements from the edge of the solar system, lost because the antenna drifted. Keeping that aim requires the Attitude and Articulation Control System, the AACS. Engineers don't usually name systems with poetry in mind, but this one describes exactly what it does. Attitude means orientation in space, which way the spacecraft is facing. Articulation means movement, the ability to adjust that orientation. The AACS uses gyroscopes to sense rotation and small hydrazine thrusters to correct it. Simple concept, brutal execution. The gyroscopes spin inside Voyager, measuring any change in orientation. When Voyager starts to drift, the gyroscopes detect it. They send signals to the flight computer. The computer calculates which thrusters to fire and for how long. Then comes the correction. The thrusters on Voyager fire for milliseconds. Puffs of gas so brief you couldn't time them with a stopwatch. These tiny puffs rotate a spacecraft the size of a car across billions of kilometers. It's like trying to turn a cathedral by whispering at it. Except it works. The cathedral turns. Each thruster firing uses hydrazine. Voyager launched with a limited supply. After 47 years, that supply is running low. Mission controllers treat every correction like spending from a savings account that can never be refilled. Fire the thrusters too often and the fuel runs out. The spacecraft tumbles. The antenna loses Earth, but fire them too rarely, and drift accumulates. Same outcome, same silence. The pointing requirement gets more absurd when you visualize it. Voyager's antenna must stay pointed at Earth within 0.1 degrees. Stand in Los Angeles and keep a laser pointer trained on a specific window in New York. You're both moving. The Earth is rotating. The Sun is orbiting the galaxy. Do it for 47 years without ever losing the target. That's what Voyager does. Every single day, with hardware designed in the 1970s using gyroscopes that were state-of-the-art when Nixon was president. Those gyroscopes drift over time. It's inevitable. Mechanical parts wear. Lubricants degrade. The drift is tiny, measured in fractions of a degree per year, but it accumulates. Engineers compensate by uploading new calibration data. They tell Voyager what its gyroscopes should be reading versus what they actually read. The difference gets stored in memory. The flight computer adjusts its calculations accordingly. This works until the drift becomes too large to calibrate. We don't really know how much longer the gyroscopes will stay calibrated. There's no manual for running a spacecraft this old. Every year past its design life, Voyager is in uncharted territory. That's the honest answer. We're guessing. Educated guessing, but guessing nonetheless. Here's something stranger. Voyager doesn't know where Earth is. Not really. It knows where the Sun is. That bright point of light that never moves much in its field of view. Engineers tell Voyager where to point relative to the Sun, and Voyager trusts that Earth will be there. It's navigating by proxy, using the Sun as a reference point because Earth is too dim and small to see from interstellar space. Voyager is pointed at where we tell it will be, trusting across 22 light hours that we calculated correctly. The spacecraft aims at a prediction, a coordinate in space where Earth should be when the signal arrives. And somehow, after 47 years, after billions of kilometers, the prediction keeps working. The antenna stays locked. The data keeps flowing. That data arrives at Earth as the weakest whisper imaginable. The Deep Space Network receives it. 3 complexes spaced around Earth, California, Spain, Australia. Each one has 70-meter dishes, 70 meters across. Picture a satellite dish the size of a baseball diamond, pointed at a single spot in the sky, collecting photons from a transmitter, 20-watt transmitter, 15 billion miles away. The signal reaches Earth at about 10 to the power of negative 16 watts. That's 0.00000000000001 watts. When Voyager's signal reaches Earth, it's so weak that if you collected all the radio energy Voyager has transmitted over 47 years, it wouldn't be enough to power a single LED nightlight for 1 second. Everything we know about the outer planets and the edge of the solar system came from less energy than it takes to toast bread. The 70-meter dishes can detect that signal because they're extraordinarily sensitive and because Voyager's antenna focuses its transmission into such a narrow beam. But there's no margin for error. If Voyager's antenna drifts off target, the signal strength drops below the detection threshold. The deep space network loses lock. Controllers send commands to correct the pointing, but those commands take 22.5 hours to reach Voyager. Another 22.5 hours for Voyager's response to return. 45 hours round trip, nearly 2 days to know if the correction worked. You can't fly a spacecraft with a 2-day delay using quick reflexes. Every command has to be perfect. Every thruster firing calculated months in advance. The power budget makes it worse. Remember those RTGs losing 4 watts per year? That declining power means fewer systems can run simultaneously. Running the thrusters requires powering the AACS computer, the gyroscopes, the thruster heaters to keep the hydrazine from freezing, and the telemetry system to confirm the correction worked. All of that draws power that could be running science instruments instead. Every time Voyager adjusts its attitude, science stops. The instruments shut down. The spacecraft focuses entirely on pointing, on maintaining that tenuous thread of communication across 22.5 billion kilometers of empty space. Engineers have gotten creative. They've reprogrammed Voyager to use older, simpler backup thrusters that haven't fired in decades. In 2017, they tested thrusters that last fired in 1980 during the Saturn encounter. 37 years dormant. The engineers sent the command, waited 22.5 hours. The thrusters fired. Perfect pulses. Exactly as programmed. Hardware built before the personal computer, sitting in interstellar space at negative 270 degrees Celsius, executing commands flawlessly after nearly 4 decades of silence. The backup thrusters bought Voyager a few more years, maybe until 2025. Then those thrusters will degrade too, and there are no more backups. This entire system, this constant battle to stay pointed, exists for one purpose: to keep Voyager talking, to ensure that whatever it detects out there in interstellar space, whatever measurements it takes at the boundary of the sun's influence, actually reaches us. The data means nothing if it can't be transmitted. The discoveries vanish if the antenna drifts. So Voyager holds its aim, millisecond by millisecond, thruster pulse by thruster pulse, pointing at a blue dot it cannot see, trusting that we're still there, still listening, still waiting to hear what it found at the edge of everything we've ever known. All that work to stay connected, all that engineering to keep the signal flowing. It was for this, for the moments when Voyager crossed boundaries nobody had ever touched before. The first boundary came in December of 2004. Voyager One was 94 astronomical units from the Sun. That's 94 times the distance from Earth to the Sun. If you could drive that distance at highway speed, never stopping, it would take you more than 1,000 years. Voyager had been traveling for 27 years just to reach this point. The spacecraft's instruments detected something changing. The solar wind, that constant stream of charged particles rushing outward from the Sun, suddenly slowed. Not gradually, abruptly. For 94 astronomical units, the solar wind had been screaming outward at 1,000,000 miles per hour, faster than sound could travel through that plasma medium. Then it hit a wall it didn't know was there. This was the termination shock, the place where the solar wind goes from supersonic to subsonic. Picture a shockwave, but in reverse. The solar wind doesn't stop. It just chokes. It's pushing against something that pushes back, the interstellar medium, the stuff between stars, hydrogen atoms, cosmic rays, magnetic fields left over from stars that died millions of years ago. That medium has its own pressure, and here, 94 astronomical units out, the pressure equalizes just enough to slow the solar wind down. The sun's breath goes supersonic for 94 astronomical units. Then it slows. Not because something stopped it, but because it's pushing against the galaxy itself. Voyager 2 crossed the termination shock in August of 2007, 84 astronomical units out, 10 astronomical units closer than Voyager 1. The boundary isn't a sphere. It's asymmetric, lopsided. The heliosphere, the bubble of the sun's influence, is stretched like a teardrop. On the side, facing the direction the solar system is moving through the galaxy, the boundary is closer. On the trailing side, it extends farther. Voyager 2, taking a different path, hit the shock earlier. Both spacecraft entered a new region, the Helios Heath, the space between the termination shock and the true edge of the sun's domain, a buffer zone where the solar wind is still there, still flowing, but slowed, turbulent, mixed with the first whispers of interstellar space. Imagine you're underwater, swimming up toward the surface. You can't see the surface. The water looks the same all around you, but you can feel the pressure changing. The light is different. You're approaching something. You're in between. The Helios Heath is about 28 astronomical units, thick at the nose of the heliosphere. That's where Voyager 1 crossed. 28 astronomical units, 6 times the distance from the Sun to Neptune. The buffer zone between the Sun's domain and interstellar space is wider than most of the solar system we grew up learning about. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. All of that fits in less space than the thickness of this boundary region. Voyager 1 spent nearly 8 years crossing the Helios Heath, 8 years in the transition zone. The instruments measured the solar wind density dropping, cosmic rays increasing. Particles from outside the solar system, from supernovae and neutron stars light years away, became more common than particles from the Sun. The spacecraft was leaving home, slowly, incrementally, 1 astronomical unit at a time. Then, in August of 2012, something changed again. The plasma wave instrument detected a shift. The cosmic ray detector spiked. The density of particles around the spacecraft suddenly increased by a factor of 40 times more particles. But they weren't solar wind particles. They were electrons from interstellar space, cold, ancient, not from our Sun. Voyager 1 had crossed the heliopause, 122 astronomical units from the Sun, the boundary where the pressure of the solar wind equals the pressure of the interstellar medium. Not a wall, not a line. A transition zone where one thing becomes another, where solar becomes interstellar. You break through and you're in air, different air, thinner, colder, but unmistakably different. This was it, the edge of the Sun's domain, the place where the Sun's influence ends and the galaxy begins. No spacecraft had ever been there before. No human-made object had ever left the heliosphere. Voyager 1 was in interstellar space, still inside the Oort cloud, still technically bound by the Sun's gravity, but surrounded by the medium between stars, the stuff that fills the galaxy, the ocean we swim through as a solar system. Voyager 2 crossed the heliopause in November of 2018, 119 astronomical units out, 3 astronomical units closer than Voyager 1. Both spacecraft, taking different paths, had found the edge. And the edge was exactly where the models predicted, give or take a few astronomical units, which at this scale means give or take 500 million miles. The universe doesn't care what we find convenient. But here's the thing nobody tells you. The heliopause isn't smooth. It isn't constant. It breathes. The Sun goes through an 11-year solar cycle. During solar maximum, when the Sun is most active, the solar wind is stronger. The heliopause expands outward. During solar minimum, when the Sun is quiet, the solar wind weakens. The interstellar medium pushes back harder. The heliopause contracts, pulled inward by billions of kilometers. The boundary moves, in and out, like a lung expanding and contracting. Voyager One might have crossed into interstellar space, then been pulled back into the heliosheath as the boundary moved, then crossed again. We think the 2012 crossing was the final one. We're fairly certain, but we can't be completely sure. The edge of the solar system is not a fixed place. It's a dynamic boundary, a membrane between two pressures that are constantly shifting. Think about that. The finish line moved while Voyager was crossing it. The spacecraft traveled for 35 years to reach a boundary, and the boundary itself was in motion, like trying to touch the surface of the ocean while waves are rolling past. You break through, but the surface keeps moving. Was that wave the surface? Or the next one? Or the one after that? The scientists analyzed the data for months before announcing the crossing. They wanted to be sure. They waited for multiple instruments to agree. They looked for the signature of interstellar plasma, the distinct frequency that only appears outside the heliopause. They found it. Voyager One was out, beyond the sun's wind, beyond the protective bubble we've lived inside our entire existence as a species. And Voyager Two confirmed it 6 years later. Different path, different instruments working. Same result. The heliopause is real. The boundary exists. And now we know exactly what it looks like when you cross it. A sudden jump in particle density, a shift in magnetic field orientation, the disappearance of solar wind particles, the arrival of galactic cosmic rays. Interstellar space has a signature, and Voyager found it. 122 astronomical units. That's how far you have to go to leave the sun's domain. Not to leave the solar system entirely, not to escape the sun's gravity, just to reach the place where the solar wind stops and the galaxy begins. The place where our local bubble meets the cosmic ocean. And Voyager is out there right now, still sending data, still measuring the interstellar medium, still traveling outward at 38,000 miles per hour, 17 kilometers per second, moving away from the sun, away from the heliopause, deeper into the space between stars. But how deep does that space go? How far to the next island in this cosmic ocean? The heliopause is not the edge of the solar system. That boundary is just where the sun's wind stops pushing, where our star's breath finally gives out and the galaxy begins. But the sun's gravity? That reaches much, much farther. And everything still caught in that gravitational grip is technically still part of our solar system. Think of it this way. Crossing the heliopause is like walking out your front door and calling it a cross-country road trip. You're outside, technically, but you haven't left the property. The Oort cloud is the actual property line, and it's 1,000 times farther away. Voyager has walked to the end of the driveway. It has 30,000 years of walking before it reaches the road. The Oort cloud is a shell of icy bodies surrounding the sun, trillions of comets and fragments, leftovers from when the solar system formed. It starts around 2,000 astronomical units from the sun. That's where the inner edge begins. The outer edge extends to 100,000 astronomical units, maybe farther. We're not completely sure because we've never actually seen it. We've only seen the comets that occasionally fall inward from that distant realm. Voyager One crossed the heliopause at 122 astronomical units. It's now about 160 astronomical units from the sun. That means it won't reach the inner edge of the Oort cloud for another 300 years. 3 centuries from now. Longer than the United States has existed as a country. Longer than humans have had steam engines or electricity or flight. And reaching the inner edge isn't the same as leaving. The Oort cloud is nearly 100,000 astronomical units thick. Voyager One is traveling at 17 kilometers per second. At that speed, it will take 30,000 years to pass through the entire cloud and finally truly leave the solar system's gravitational domain. 30,000 years. Humans invented agriculture 12,000 years ago. We built the pyramids 4,500 years ago. The entire span of recorded human history is only about 5,000 years. Voyager will need 6 times that long just to escape the sun's outermost gravitational boundary. Let's talk about speed for a moment. Voyager 1 is moving at 61,000 kilometers per hour. That's 16 times faster than a rifle bullet. It's 50 times faster than the speed of sound. It's one of the fastest objects humans have ever made. A piece of human engineering screaming through the void faster than almost anything we've ever launched. And at that speed, it would take 73,000 years to reach Proxima Centauri, the nearest star. 73,000 years. Humans have had written language for 5,000 years. Anatomically modern humans have existed for 300,000 years. Voyager would need to travel for 1/4 of the entire span of human existence to reach the closest star. If Voyager had launched when the first humans left Africa, it would be only 1/4 of the way there. Proxima Centauri is 268,000 astronomical units away. That's 4.24 light years. Light takes 4 years and 3 months to cover that distance. Light, which crosses the gap between Earth and the Moon in 1 second. Light, which could circle the Earth 7.5 times in that same second. Even light needs more than 4 years to reach the nearest star. Voyager isn't heading toward Proxima Centauri. It's not heading toward any particular star. Actually, it's heading into the space between stars, the emptiness itself. In 40,000 years, it will pass within 1.6 light years of a red dwarf called Gliese 445. That's the closest it will ever come to another star. And 1.6 light years is still 100,000 times farther than Voyager is from the Sun right now. 1.6 light years. That's the nearest approach Voyager will make to anything. Not a close encounter. Not even remotely close. Just slightly less distant than the infinite emptiness surrounding it. Here's what that means. Voyager's destination isn't a star. It's the void itself. It will spend the rest of its existence, millions of years, billions of years, traveling through the emptiest places in the galaxy. The mission is called interstellar, but the reality is intergalactic emptiness. A journey to nowhere, through nothing, forever. The spacecraft will outlast human civilization. It will outlast the Earth as a habitable world. The Sun will expand into a red giant and consume the inner planets, and Voyager will still be out there, coasting through the dark, silent by then. Its power source long dead, its instruments frozen, but still moving, still heading away. That's the scale we're dealing with. Crossing the heliopause wasn't the end of Voyager's journey. It was barely the beginning. The probe has left the Sun's wind, yes. It's in interstellar space, yes. But it hasn't left home. Not really. Not in any meaningful gravitational sense. It's in the driveway, the long, cold driveway that stretches for 30,000 years. And beyond that driveway is a road that goes on forever, passing nothing, reaching nowhere, extending into a darkness so complete and so vast that even our fastest creation will spend eternity as a mote of dust drifting between islands of light. The heliopause was a milestone, a real boundary that Voyager crossed and measured and sent back data about. But the solar system, the Sun's true domain, that stretches 1,000 times farther. And the distance to the stars? That's another 1,000 times beyond that. So when we say Voyager has left the solar system, we mean something very specific. It has left the bubble of solar wind. It has entered the interstellar medium. But it's still bound to the Sun, still orbiting, technically, in a vast ellipse so wide it will take millennia to trace. And the space beyond, the true interstellar void, that's where Voyager is heading. Not toward light, toward darkness, the space between. Let me tell you what that space looks like, the space between. Imagine a cathedral, vaulted ceilings, stone columns stretching toward light, the vast interior filled with air and silence. There are about 2.5 times 10 to the 19th atoms in every cubic centimeter of that air. That's 25 billion atoms in a space the size of a sugar cube. The air is thick with molecules, oxygen, nitrogen, carbon dioxide. You breathe it, you move through it. It pushes back against your skin with 14 pounds of pressure per square inch. The interstellar medium has 0.1 atoms per cubic centimeter. If you scaled interstellar space to that same cathedral, there would be 1 atom inside. 1. Not 1 atom per cubic meter. One atom in the entire cathedral, and that atom would take years to drift from the altar to the door. This is the space Voyager is traveling through. This is what's between the stars. Not darkness, emptiness. A void so complete that calling it empty feels insufficient. At sea level on Earth, you're surrounded by 10 to the 19th atoms per cubic centimeter. In interstellar space, Voyager encounters 0.1. That's a difference of 100 billion to 1. The emptiest vacuum chamber ever built on Earth is 1,000,000 times denser than the space Voyager is in right now. This is the part that gets me. Not the distance, not the time, the emptiness. We built something that could survive the emptiest places in the universe, and then we sent it there on purpose. We aimed it at nothing and called it exploration. The void is made mostly of hydrogen. 90% of the atoms out there, when you find one, are hydrogen. 9% are helium. Everything else, carbon, oxygen, iron, silicon, all the elements that make planets and people, they account for 1%. One atom in 100 is something other than the simplest elements in the universe. Interstellar space is the remnant of creation, the primordial gas that never collapsed into stars, still drifting, still waiting. The temperature is 3 Kelvin, 3 degrees above absolute zero, the coldest possible temperature in physics. That's negative 270 degrees Celsius, negative 454 degrees Fahrenheit. Numbers that cold stop meaning anything until you compare them to something real. Pluto's surface gets down to about 40 Kelvin. The shadowed craters at the lunar south pole, the ones that never see sunlight, they reach about 30 Kelvin. Interstellar space is 10 times colder than that. It's colder than anything naturally occurring inside the solar system, colder than the darkest, most forsaken place on any world orbiting the sun. Voyager is in the coldest environment it has ever experienced, and it will stay that cold for the rest of time. The spacecraft was built in California, assembled in clean rooms where engineers wore lab coats, and the air was filtered and temperature controlled. It launched from Florida in summer heat. It flew past Jupiter, where the cloud tops churn at negative 140 degrees Celsius. It passed Saturn, Neptune, the frozen edges of the Kuiper Belt, and now it's somewhere colder than all of that, 3 degrees above the point where atoms stop moving, where matter itself runs out of energy. The universe has a basement temperature, and Voyager is there, but the cold isn't trying to kill it. That's the strange part. There's nothing to conduct heat away. No air, no medium. Voyager radiates heat into the void. Yes, but slowly. The emptiness insulates as much as it freezes. The probe's radioactive power source keeps its instruments warm enough to function. Barely. A tiny island of warmth drifting through absolute cold. The cosmic rays are different now. Inside the heliosphere, the solar wind acts as a shield, deflecting most cosmic rays. Outside, there is no shield. Voyager is exposed to the full flux of particles accelerated to near light speed by supernovae and black holes across the galaxy. Every second, thousands of cosmic rays pass through Voyager's instruments. They're protons, mostly. Atomic nuclei stripped of electrons and flung across space at 99% the speed of light. Some of them have been traveling for 1,000,000 years. Some of them started their journey when your ancestors were still learning to walk upright. It's like standing in a rainstorm, except the raindrops are moving at 99% the speed of light, and they've been falling for 1,000,000 years. The cosmic ray flux is 10,000 times higher than it was inside the heliosphere. 10,000 times. Voyager's instruments register the change. Particle detectors that spent decades measuring the solar wind now count impacts from across the galaxy, radiation from stars that died before Earth formed, energy from collisions that happened in other spiral arms, thousands of light years away. The universe is shooting at Voyager, not with intent, just with the ambient violence of deep space. And Voyager is recording every hit. The interstellar magnetic field threads through the void, about 0.3 nanotesla in strength. That's 3 billionths of the magnetic field you experience standing on Earth's surface. But it's there, a faint structure woven through emptiness. The field lines run parallel to the galactic plane, shaped by currents of charged particles flowing between the stars. Voyager can measure it. Barely. The magnetometer picks up fluctuations, waves in the field that propagate like ripples on water, except the water is a plasma, so diffuse it might as well not exist. There's dust out there too, grains of silicate and carbon, ice, the debris of dead stars ground down to particles smaller than smoke. On average, you'd find one grain every few astronomical units, every few times the distance from Earth to the Sun, one speck of dust. Voyager might encounter a dozen grains per year, most of them smaller than bacteria, traveling at 10 kilometers per second relative to the spacecraft. When they hit, they vaporize. A tiny flash of heat and light that's over before it begins. The solar wind is gone, completely. Voyager's plasma instruments used to detect a constant stream of particles from the Sun, protons and electrons blown outward at 400 kilometers per second. That flow defined the heliosphere. It was the Sun's breath, the exhalation that carved out a bubble in interstellar space. Voyager spent 35 years inside that breath, and then it stopped. The instruments went quiet. Not broken, just nothing left to measure. The wind doesn't reach here, but here's what I can't shake. The thing that stays with me. The void isn't empty. Not truly. It's filled with photons, ancient light from the Big Bang, the cosmic microwave background radiation that permeates all of space. Voyager is bathed in the afterglow of the universe's birth, photons that have been traveling for 13.8 billion years. They've cooled as space expanded, stretched from visible light to microwaves, but they're still there, still moving. The void contains the memory of creation itself, and Voyager is swimming through it, recording faint traces of the oldest light in existence. Every second, billions of these photons pass through Voyager's hull, ghosts of the Big Bang washing over 1970s technology. The spacecraft was built in an era of analog circuits and magnetic tape. It was launched before personal computers, before the internet, before anyone knew what the cosmic microwave background really looked like in detail. And now, that same machine is surrounded by it, moving through the fossil light of creation. The emptiness is full of the past. Think about that. The void between stars isn't nothing. It's a thin gas of primordial hydrogen, a magnetic field woven by galactic currents, cosmic rays from dead stars, dust from supernovae, and the light of the Big Bang itself, cooled and stretched, but still present, still filling every cubic centimeter of space with photons that remember when the universe was young and hot and dense. Voyager is measuring all of it: the density, the temperature, the magnetic field, the cosmic rays. This is what emptiness actually looks like when you send instruments to examine it. Not a void, a medium, thin beyond comprehension, cold beyond experience. But there, real, measurable. The space between stars has structure. It has properties. It has a composition and a temperature and dynamics we're only beginning to understand. And somewhere in that vast, cold, nearly empty expanse, a machine we built is taking notes, counting atoms, recording magnetic field fluctuations, detecting particles that have crossed the galaxy. It's out there now, in the cathedral with one atom, drifting through the afterglow of creation, and it's telling us what it finds. The plasma wave instrument listens to space, not metaphorically. It detects actual oscillations, actual waves in the charged particles around the spacecraft. When Voyager crossed the heliopause, the pitch changed. The waves went from solar origin frequencies to interstellar frequencies, like walking from a room where someone's humming to a room where someone else is humming a different note. Voyager heard the difference. That's how we knew it had crossed, not by seeing a boundary, but by listening to the change. The instrument itself is simple: an antenna extending from the spacecraft's body, a sensor measuring voltage fluctuations in the plasma around it. When charged particles oscillate, they create electromagnetic waves. The plasma wave subsystem detects those waves and records their frequency and amplitude. It's reading the electrical environment of space the way a seismometer reads vibrations in the ground. On August 25, 2012, the frequencies changed. The plasma waves Voyager detected shifted to higher frequencies. Denser plasma, different composition. The spacecraft had crossed from the heliosphere into the interstellar medium, and the plasma wave instrument registered the transition in real time. Engineers back on Earth saw the data weeks later, after it traveled 14 billion miles at the speed of light. They looked at the frequency shift and knew Voyager was through. Here's the thing, the plasma wave instrument wasn't designed to detect interstellar plasma. It was designed to study plasma waves around Jupiter and Saturn. Engineers repurposed it for the interstellar mission, using an instrument built for planetary encounters to measure the space between stars. Most of Voyager's interstellar data comes from instruments doing jobs they were never meant to do. The mission succeeded because engineers improvised, reinterpreted, and adapted decades-old technology to answer questions that hadn't been asked when the instruments were built. The cosmic ray detector works differently. It measures high-energy particles, mostly protons, flying through space at nearly the speed of light. These particles come from supernovae, from active galactic nuclei, from events so violent they accelerate matter to relativistic speeds. Inside the heliosphere, the sun's magnetic field deflects many of these particles. Outside, there's no shield. Cosmic ray intensity jumps. That's exactly what Voyager measured. As it approached the heliopause, cosmic ray counts increased. After it crossed, they stayed high. The spacecraft went from a region where the sun's influence dominated to a region where galactic processes took over. The cosmic ray detector quantified that transition. More hits per second, more high-energy particles. The galaxy made itself known through radiation. The magnetometer measures magnetic field strength and direction. It's a sensor on a boom, far enough from the spacecraft that Voyager's own magnetic signature doesn't interfere. The instrument takes readings constantly: direction, intensity, fluctuations. In the heliosphere, it measured the sun's magnetic field, carried outward by the solar wind. In interstellar space, it measures the galaxy's magnetic field, a different structure, different strength, different origin. The transition wasn't instant. The magnetic field shifted gradually as Voyager moved through a transition region where solar and interstellar influences mixed. The magnetometer recorded every step of that shift. Engineers used the data to map the heliopause's structure, its thickness, its dynamics. The boundary isn't a wall, it's a zone, turbulent, complex. The magnetometer gave us our first direct measurements of what that zone actually looks like. These three instruments together painted the picture of crossing. Plasma waves changed frequency, cosmic rays increased, the magnetic field reoriented. Each instrument told part of the story. Combined, they confirmed what no spacecraft had ever done before. Voyager had left the sun's domain, and they're still working, still taking measurements. The plasma wave instrument still listens to interstellar oscillations. The cosmic ray detector still counts particles. The magnetometer still reads the galaxy's magnetic field. 46 years after launch, instruments designed in the 1970s are measuring conditions no human has ever measured before. But keeping them running requires constant work. In 2022, Voyager One started sending corrupted data from its attitude control system. Engineers spent months diagnosing the problem from 159 astronomical units away. 1 astronomical unit is the distance from Earth to the Sun, about 93 million miles. 159 of those. The communication delay is 22 hours one way. Send a command. Wait 22 hours for it to reach Voyager. Wait 22 more hours for the response. Every diagnostic cycle takes nearly 2 days. Then they uploaded a software fix. New code, remotely installed, into a computer built in the 1970s that's been running for 45 years. It's like remotely reprogramming someone's brain during surgery, across a 22-hour communication delay, using equipment older than most surgeons. And it worked. The corrupted data stopped. The attitude control system resumed normal operation. A spacecraft at the edge of the solar system was debugged and patched by engineers who weren't born when it launched. Cosmic rays occasionally flip bits in Voyager's memory, change a 0 to a 1 or vice versa. The spacecraft has error-checking routines, but sometimes a bit flip happens in a critical location and the spacecraft gets confused. It's being slowly corrupted by the environment it's measuring, one bit at a time, like a book being rewritten by the rain that's falling on it. Engineers have uploaded memory resets multiple times, clearing corrupted sections, restoring clean code, maintaining functionality in a system that's under constant bombardment from the particles it's trying to count. Every software update is a calculation. Each transmission uses power. Each change risks introducing a new problem. Engineers weigh every fix against the spacecraft's dwindling resources. But they keep doing it. They keep uploading patches, recalibrating sensors, adjusting parameters, because the instruments are still working, still detecting, still measuring the interstellar medium that no other human-made object has ever touched. Think about what that means. We're operating scientific instruments at a distance where light takes almost a full day to travel. We're debugging software on a computer with 64 kilobytes of memory, less than a single digital photo. We're maintaining a spacecraft that's older than most of its current operators, and it's still sending data, still telling us what's out there in the space between stars. The plasma oscillations continue. The cosmic rays keep coming. The magnetic field shifts and flows, and Voyager listens, counts, and measures. Out there in the cathedral with 1 atom per cubic centimeter, in the thin gas that fills the galaxy, the instruments keep working because engineers keep them working. One software upload at a time, one recalibration at a time, one bit flip correction at a time, maintaining contact with a machine that's measuring what emptiness actually sounds like when you listen closely enough. Emptiness has a sound. Voyager has heard it. The plasma wave instrument doesn't just detect the thin gas between stars. It listens to events happening across distances that make the solar system look small. When the sun erupts, when massive coronal mass ejections tear away from its surface and race outward at 1,000,000 miles per hour, Voyager can hear them arrive at the heliopause, the boundary between our sun's influence and interstellar space, the edge of everything we've ever known. It takes time. A coronal mass ejection leaves the sun, and we detect it here at Earth almost immediately. The plasma slams into our magnetosphere. Auroras dance. Satellites go into safe mode. Then that same ejection keeps traveling outward, past Mars, past Jupiter, past Neptune, past everything. 10 months later, sometimes 12, it reaches the heliopause, 120 astronomical units from home, 120 times the distance from Earth to the Sun. When a coronal mass ejection from the Sun reaches the heliopause, it's like throwing a rock into a pond and watching the ripples spread. Except the pond is 120 astronomical units wide. The rock is 1 billion tons of plasma traveling at 1,000,000 miles per hour, and the ripples take a year to arrive. Voyager sits on the far shore of that pond, feeling the waves arrive, counting the months since the Sun threw the rock. The plasma wave instrument detected 2 major events: November 2012, April 2013, both coronal mass ejections that originated at the Sun more than a year earlier. Both created oscillations in the interstellar plasma that Voyager could measure. The frequencies changed. The density shifted. For weeks, the instrument recorded plasma waves rippling through the space between stars, triggered by an eruption that happened back when Voyager was still inside the heliosphere, still technically in the Sun's domain. Think about that timeline. An explosion on the Sun. Earth gets the news in hours. Voyager gets it a year later. We can correlate the events. Match the plasma oscillations Voyager detects to specific eruptions we observed from Earth. The Sun sneezes, and a year later, Voyager hears the echo at the edge of everything. When a massive ejection hits the heliopause, the entire boundary vibrates. The heliosphere rings like a bell that's 250 astronomical units across. Voyager's plasma wave instrument can hear it, a low-frequency hum that lasts for months as the boundary settles. We're listening to the Sun's sphere of influence, resonating like a struck gong, and the sound takes a year to reach us. 250 astronomical units. That's the rough diameter of the heliosphere, counting both sides. The distance from the Sun to the heliopause in one direction, then the same distance in the opposite direction, 23 billion miles across. A bubble of solar wind and magnetic fields and charged particles, all carved out by our star, pushing against the interstellar medium. And when it gets hit hard enough, it rings. The oscillations aren't random. They follow patterns. Scientists can analyze the frequencies and learn about the plasma density, the magnetic field strength, the temperature of the interstellar medium. Each ringing event is a measurement opportunity, a chance to probe the space between stars using the Sun's own violence as the instrument. But the coronal mass ejections aren't the only phenomena Voyager detects. The plasma density varies. Sometimes it increases, sometimes it drops. Some of these variations might be local turbulence in the interstellar medium, eddies and currents in the thin gas. Some of them might be shock waves from supernovae, stars that exploded thousands or millions of years ago, sending compression waves through the interstellar medium that are still traveling, still spreading. Voyager might be detecting the echoes of stellar deaths that happened before humans existed, before Earth had multicellular life, ancient explosions, still making waves. We can't know for certain. The data shows density variations, but pinpointing the source requires more information than Voyager can provide. Maybe it's a shockwave from a supernova that detonated 10,000 years ago, when humans were just figuring out agriculture. Maybe it's something else entirely. The interstellar medium isn't uniform. It's lumpy, textured, shaped by millions of years of stellar winds and explosions and the slow churn of galactic rotation. The magnetic field measurements add another layer. Voyager's magnetometer shows the direction and strength of the galactic magnetic field, the field that threads through the spiral arms of the Milky Way, connecting star systems across thousands of light years. It's weak, incredibly weak compared to Earth's magnetic field, but it's there, and Voyager can measure it. The direction matters. The galactic magnetic field runs roughly parallel to the plane of the galaxy, following the spiral arms. Voyager's measurements confirmed the orientation, confirmed that we're now in a region where the Sun's magnetic field no longer dominates. The galaxy's field has taken over. We've crossed into territory shaped by forces larger than our star. When Voyager's plasma wave instrument detects these events, we can convert the frequencies to audio, actual sound waves humans can hear. NASA has released recordings of what the heliopause crossing sounds like, what the interstellar plasma sounds like. It's eerie, a low hum punctuated by bursts of static when coronal mass ejections arrive. These aren't metaphorical sounds. They're actual oscillations in plasma, scaled to frequencies we can hear. Voyager is listening to interstellar space, and we can listen too. The void has a voice, and it sounds like distant thunder that never stops. It's oddly calming, the sound of interstellar space. You'd think it would be dramatic, cosmic, something worthy of a movie soundtrack. Instead, it sounds like you left a radio on between stations in a basement at 3 in the morning. The universe is humming to itself, and mostly it sounds bored. The recordings are available online. You can listen to what Voyager hears. The plasma oscillations, the density variations, the low-frequency waves that propagate through a medium with 1 atom per cubic centimeter. 1 atom per cubic centimeter is the interstellar density near Voyager. That's emptier than the best vacuum we can create on Earth, emptier than anything in our solar system except the space between planets. And yet, it carries sound, carries waves, carries information about coronal mass ejections and supernovae and the structure of the galaxy itself. The heliosphere keeps ringing, the sun keeps erupting, coronal mass ejections keep racing outward, and 10 months later, 12 months later, Voyager detects them at the boundary, measures the plasma oscillations, records the frequencies, sends the data back across 18 billion miles of empty space so we can hear what the edge of the solar system sounds like when something hits it. We're listening to a boundary we'll never see, hearing echoes of explosions that happened before we were born, detecting waves in a medium so thin it barely exists. And the strangest part is that it works. The instruments keep detecting. The data keeps arriving. The universe keeps making noise, and Voyager keeps listening. Out there in the cathedral, with 1 atom per cubic centimeter, in the humming darkness between stars, hearing things no human ear will ever directly experience. But we can listen to the recordings. We can hear what Voyager hears, translated into frequencies our ears can process. The void isn't silent. It never was. We just needed to send something far enough to listen. We can't see Voyager, not with our best telescopes, not with anything we have. The spacecraft is the size of a small car, and it's 159 astronomical units away. 1 astronomical unit is the distance from Earth to the Sun, about 93 million miles. So Voyager is 159 times that distance. Trying to image it from Earth is like trying to photograph a grain of sand in Los Angeles from New York at night, with the grain of sand painted black. It reflects no light. It generates no light. It's invisible. The only reason we know it exists is that it's still calling home, sending a signal so faint we need a 70-meter dish just to hear it. We can't see Voyager. We can only listen for it. Trust that it's out there because the data keeps arriving. The numbers keep updating. The signal keeps reaching across 18 billion miles of space to tell us it's still alive. Voyager can't see us anymore either. Not really. From where it is now, the sun is still the brightest thing in the sky, but it's just a bright star. No disk visible, no warmth, just a point of light among other points of light. And somewhere in the glare of that star, invisible, is Earth. Voyager is calling to a planet it can no longer see, trusting we're still there to listen. That relationship, that's what we have now. 2 objects separated by such distance that neither can see the other. Only the radio signal connects us, a whisper across the void, as mentioned back when Voyager first crossed into interstellar space. The spacecraft and its home planet, blind to each other, communicating through invisible waves. It wasn't always like this. There was a moment when Voyager could still see Earth, when the cameras were still on. February 14th, 1990. Voyager 1 was 6 billion kilometers from home. That's 40.5 astronomical units, about 4 times the distance from the Sun to Neptune. From there, mission controllers commanded the spacecraft to turn around, to look back at the solar system, one last time, to take a family portrait of the planets. Earth appears in one of those images, a pale blue dot suspended in a ray of scattered sunlight. The planet is 0.12 pixels, not even a full pixel, a fraction of one. Every human who has ever lived, every city, every war, every love story, every invention, compressed into 12% of a pixel. Carl Sagan called it a mote of dust suspended in a sunbeam. That's generous. It's not a mote. It's a fraction of a mote. It's the idea of dust. Think about that scale for a second. The image was taken from 40.5 astronomical units. Voyager 1 is now about 160 astronomical units away, 4 times farther than when the pale blue dot was taken. If Earth was barely visible then, a sliver of a pixel in the camera, it would be completely invisible now, lost entirely in the sun's glare. Even if the cameras were still working, even if we commanded Voyager to turn and look, there would be nothing to see. The cameras aren't working. They were shut down right after that family portrait to conserve power. Voyager would need every watt for the instruments, for the plasma detectors and magnetometers, for the systems that could still do science. The cameras had done their job, seen Jupiter and Saturn and Uranus and Neptune, captured moons and rings and storms. There was nothing left to photograph in the darkness ahead, just empty space. So the imaging system was powered down forever. That photograph, the pale blue dot, almost didn't happen. Carl Sagan had to fight for it. Engineers argued it was a waste of resources. The cameras weren't needed for the extended mission. Pointing the spacecraft back toward the inner solar system risked exposing sensitive instruments to sunlight. The image wouldn't reveal any new science. It was just a picture, just a sentimental gesture. Sagan insisted anyway. He argued for the philosophical importance of seeing Earth from the edge of the solar system, of witnessing our place in the cosmos from that distance. He won the argument. Voyager turned, the cameras activated, the shutter opened, the image was captured and transmitted back to Earth. Then the cameras were shut off forever. That photograph, one of the most iconic images in human history, happened only because one person argued we needed to look back, even if just once, even if it served no scientific purpose, even if it was just to see ourselves as we really are, small, fragile, alone in the dark. From our perspective now, Voyager is invisible, a machine we built and launched and lost to the darkness. We know where it is because we can calculate its trajectory. We know it's there because the signal keeps coming, but we can't see it, can't image it, can't point a camera at that region of space and pick out the spacecraft against the stars. From Voyager's perspective, if it had eyes, if it could still turn its cameras toward home, we would be invisible too. Earth would be drowned in the light of the sun, a planet lost in the glare of its own star. The spacecraft left us behind decades ago, crossed into a realm where we're just a memory, a direction, a target for the radio dish. We're both out there in the dark, both invisible to each other, connected only by a signal that takes 22.5 hours to cross the distance one way, 45 hours for a round trip. Send a command, wait nearly 2 days to find out if it worked, ask a question, wait nearly 2 days for an answer. The conversation moves at the speed of light, and it's still achingly slow. The pale blue dot image reminds us what that distance means. When Earth is a fraction of a pixel from 40.5 astronomical units, what are we from 160? Less than a fraction. An idea, a concept, a place Voyager remembers but can no longer confirm exists. It keeps sending data back to coordinates in space, trusting that when the signal arrives, someone will be there to receive it, that the 70-meter dishes will be pointed in the right direction, that humanity is still listening. We are, for now. The Deep Space Network tracks Voyager every day, receives its transmissions, decodes the data, sends commands when needed. The spacecraft calls, and we answer. It can't see us through the void. We can't see it, but the signal crosses the gap. The conversation continues. Two invisible objects, talking across the darkness, bound by invisible waves. The conversation continues, but not for much longer. Voyager's power is dying. Not suddenly, not dramatically, just steadily, predictably, like a battery running down. The spacecraft loses about 4 watts of power every year. 4 watts. That's less than a typical LED bulb. But when you're operating on 249 watts total, the power draw of an old incandescent bulb, 4 watts matters. Every year, Voyager gets a little quieter. Not the signal, the spacecraft itself. Instruments are shut down one by one, like turning off lights in a house you're leaving for the last time. First the cameras, then the ultraviolet spectrometer, then the infrared radiometer. Each year, another light goes out. By the mid-2030s, only the transmitter will remain, sending a carrier signal with no data. Then, even that will fade. The last light in the house will turn off, and Voyager will continue in darkness. The shutdown sequence has already begun. Engineers started making choices in the early 2020s. Which instruments to turn off first? Which to keep running until the very end? It's triage. Which experiments matter most in the final years? Which data is worth gathering when you only have enough power for 1, maybe 2 instruments? They're making decisions about what humanity will learn versus what we'll never know, because we ran out of power before we could measure it. Each shutdown is a door closing on a type of knowledge forever. The plasma wave instrument will probably be last, the one that detected the edge of the heliopause, the one that listens to the sound of interstellar space. Engineers want to keep it running as long as possible, because we've never had a microphone out there before. Every day it operates, we learn something new about the medium between stars. But even that instrument has a deadline. By around 2030, there won't be enough power to run any science instruments, not enough to process data, not enough to keep the systems warm enough to function properly. The science mission will end. The transmitter will last a bit longer, maybe until 2036, maybe a year or two beyond. It takes less power to send a signal than to run experiments. For a few years, Voyager will still be calling home, even though it has nothing new to say. A carrier wave, a tone, proof of existence, and nothing more. Engineers will receive it, track the spacecraft's position, monitor the signal strength. Then one day, it will stop. The final transmission from Voyager won't be dramatic. No final message, no goodbye. One day, the signal will be there, weak, faint, barely detectable by the 70-meter dishes. The next day, it won't be. Engineers will try to re-establish contact for weeks, maybe months. They'll send commands into the void. They'll point the antennas at the exact coordinates. They'll wait for a response that won't come. Then they'll accept it. The silence will be permanent. The last conversation with Voyager will end mid-sentence, and we'll never know what the last bit of data was trying to say. You might think that's the end. The power dies. The transmitter shuts down. The mission concludes. The spacecraft becomes a piece of silent metal coasting through the dark. But that's not quite what happens. After the transmitter dies, Voyager will still be working. The radioisotope thermoelectric generators will still produce power, just not enough to run the transmitter. Maybe 15 or 20 watts, maybe less. But some instruments might still operate on that trickle. The plasma wave instrument could still be listening. The magnetometer could still be measuring. The cosmic ray detector could still be counting particles. They'll be collecting data, storing it in memory, recording observations of a realm no human-made object has ever explored. But there will be no one to send it to, no way to transmit it. The transmitter needs more power than the RTGs can provide. Voyager will be conscious but unable to speak, gathering observations of interstellar space that no one will ever receive. It will have data, potentially decades of data, locked in memory forever. Measurements of the galaxy's magnetic field, recordings of plasma waves rippling through space, counts of cosmic rays from distant supernovae, all of it trapped inside a computer no one can access, flying away from Earth at 38,000 miles per hour. 38,000 miles per hour. That's fast enough to cross the United States in 7 minutes. Fast enough that every hour, Voyager puts another 38,000 miles between itself and any possibility of retrieval. It's not dying. It's being silenced. There's a difference. A dead spacecraft is inert, frozen, finished. A silenced spacecraft is still alive, still measuring, still recording, still trying to complete its mission even though no one will ever know what it found. The observations will never be downloaded. The memory will never be read. The data will travel with Voyager for billions of years, locked inside, unshared, unseen. Think about that. Decades of potential discoveries, right there in Voyager's computer. Information about what lies between the stars, about the structure of the galaxy, about the environment our solar system moves through. All of it unreachable. We'll know it's there. We'll know Voyager kept working after we lost contact, but we'll never know what it learned. Eventually, even the instruments will stop. Not because they break, necessarily, because the RTGs will decay below the threshold needed to power anything. Maybe in the 2050s, maybe the 2060s. The exact year doesn't matter. The result is the same. Voyager will go completely dark. No instruments, no transmitter, no heaters. The spacecraft will freeze to the temperature of space, around -400 degrees Fahrenheit, cold enough that metal becomes brittle, cold enough that electronics would shatter if you touched them. But Voyager will still be moving, still traveling, still coasting on the velocity we gave it in 1977. In 40,000 years, it will drift past a star called Gliese 445, not close, about 1.7 light-years away. 1.7 light-years. That's 10 trillion miles. If you drove at highway speed, it would take about 200 million years to cover that distance. Voyager won't slow down, won't stop, won't send a postcard. It will be silent then, completely silent. No hum of electronics, no warmth from the RTGs, no data being recorded. Just a shell, a relic, a monument to a civilization that once reached beyond its atmosphere and touched the space between stars. The golden record will still be attached. The instructions for playing it will still be etched on the cover, but there will be no one nearby to find it. No planets around Gliese 445 that we know of. Just empty space and a distant star. The silence is coming. Not today, not next year, but soon, on the timescale of a mission that's already lasted 47 years. By the time a child born today graduates from college, Voyager will probably be silent. By the time that child reaches middle age, Voyager will be dark. The mission that defined interplanetary exploration, the spacecraft that showed us the outer planets and then kept going, the probe that left the solar system and entered the space between stars. It will be out there, unreachable, holding data no one will ever see and memories no one will ever access. The conversation is ending. We're approaching the last words, and when they come, we won't be ready. We'll want more time, more data, more years, but the universe doesn't care what we find convenient. The power will run out, the signal will fade, the silence will begin, and Voyager will continue alone, carrying questions we'll never be able to ask and answers we'll never be able to hear. When the silence comes, when the signal fades and the power runs out, something will remain. Each Voyager carries a golden record, gold-plated copper, 12 inches across, engraved with instructions for playback. It contains 115 images of Earth, natural sounds, thunder, wind, surf breaking on a beach, birdsong, whale calls, the crackling of fire, music from across the world, Bach, Chuck Berry, a Navajo chant, a wedding song from Peru, greetings in 55 languages, hello, peace, good wishes from the children of Earth. The golden record includes Chuck Berry's Johnny B. Good. If aliens ever find Voyager and play the record, the first human music they hear will be rock and roll. I think about this more than is reasonable. Of all the things we could have said about ourselves, we said, we like guitars, we like rhythm, and we thought this riff was worth preserving for 1 billion years. Honestly, not the worst choice. The record was designed to last. Gold doesn't corrode in the vacuum of space. No oxygen to rust it. No water to wear it down. No atmosphere to erode it. The golden record will outlast everything we've ever built. The pyramids will erode to sand. The Great Wall will crumble. Every city will be reclaimed by nature, or buried under ice, or swallowed by rising seas. The golden record will still be intact, still readable, still carrying 115 images of a world that no longer exists. It's the most permanent thing humanity has ever created, and it's traveling through the emptiest places in the universe where nothing can corrode it, nothing can break it, nothing can erase it. Think about the timescale. 5 billion years from now, the sun will expand into a red giant. It will swallow Mercury. It will swallow Venus. It will probably swallow Earth. Everything we know will burn. Every ocean will boil away. Every mountain will melt. The continents will vaporize. The golden record will still be out there, intact, carrying sounds from a planet that no longer exists orbiting a star that's dying. That's 5 billion years, 5,000 million. If you started counting one number per second, never sleeping, never stopping, it would take you 158 years just to count to 5 billion. And the golden record is expected to remain readable for the entire span. But here's the thing. The golden record is like putting a message in a bottle and throwing it into the Pacific Ocean. Except the ocean is the entire Milky Way galaxy, and the bottle is the size of a car. And it's moving at 61,000 kilometers per hour through a void so empty that the chance of it passing within a light year of another star is nearly zero. The record will exist for 1 billion years. The chance of anyone finding it is functionally zero. It wasn't made to be found. It was made to be sent. That distinction matters. The golden record isn't really for aliens. It's for us. It's a statement about who we were in 1977, what we valued, what we wanted to say about ourselves. The team that assembled the record, led by Carl Sagan, chose what to include. They chose images of DNA structures and mathematical definitions and diagrams of our solar system. They chose pictures of a woman breastfeeding and a family eating dinner and children playing. They chose to say, this is what mattered to us. The record includes audio of Anne Druyan's brainwaves and heartbeat, recorded as she thought about Earth, about human history, about falling in love with Carl Sagan. There's a love story encoded on that record. Electrical impulses of someone falling in love, preserved in gold, traveling through interstellar space forever. It's the most romantic and absurd gesture in human history. She knew the recording was happening. She sat in a laboratory with electrodes attached to her head and thought about specific things. The history of Earth, the evolution of life, what it means to be human. And yes, Carl Sagan, who she'd just started falling for. Those thoughts became electrical patterns. Those patterns became audio signals. Those signals were etched into gold. Now, they're traveling at 17 kilometers per second through the space between stars. Someone falling in love, preserved forever, sent into the void. The golden record includes greetings in 55 languages, but one of them is a dead language, Sumerian, spoken 6,000 years ago in ancient Mesopotamia, extinct for millennia. The greeting is an academic reconstruction of a language no living human speaks. We sent a message to potential extraterrestrials in a language we ourselves don't understand, from a civilization that collapsed before the pyramids were built. It's a greeting from ghosts, carried by a machine into the void. Nobody alive knows exactly what that Sumerian phrase sounds like when spoken naturally. We know the words, we know the grammar, mostly, but the accent, the rhythm, the way a native speaker would have voiced it, gone, lost to time. The golden record carries a best guess from 1977 about how people spoke in 2600 BCE. It's a chain of interpretation, Sumerian to cuneiform tablets, to modern archaeological reconstruction, to audio recording, to gold-plated copper, to interstellar space. And if anyone ever plays it, they'll hear a language that stopped being spoken before writing was widespread, reconstructed by a species that might also be extinct by then, carried by a probe that's already obsolete. When Voyager's power dies, when the instruments shut down and the signal stops, the spacecraft becomes something else. Not a probe anymore, an artifact, a time capsule from 1977, carrying technology that was already outdated by the time it left the solar system. 8 track tape recorders, analog computers, the golden record itself, instructions for a turntable, on a device traveling through space where no one has turntables. It's obsolete, it's ancient, it's ours, and it will be out there longer than our species will probably exist, longer than our cities, longer than our languages. The golden record will still be traveling through the Milky Way when the English language is as dead as Sumerian, when the borders we drew are forgotten, when the nations that launched Voyager are historical footnotes, if they're remembered at all. The spacecraft won't know. It won't care. It will just keep moving, 17 kilometers per second, every year, every million years, carrying 115 images and greetings in 55 languages and the sound of someone falling in love into the galaxy forever. Voyager One and Voyager Two are humanity's first interstellar artifacts, the first objects we ever made that left the solar system entirely. They're out there now, beyond the heliopause, beyond the sun's influence, in the space between stars, and they will be out there for billions of years, long after the last human has died, long after the sun has swollen into a red giant and consumed the Earth, long after our solar system is a fading memory of what it once was. Voyager will still be traveling, silent, dark, frozen, but intact, moving through the galaxy at 17 kilometers per second, carrying a golden record with pictures of a world that no longer exists and greetings in languages no one speaks. It's not a spacecraft anymore. It's a fossil, a relic, proof that once, briefly, a species on a small planet looked up and wondered what was out there, and then built something to go find out. The continents will rearrange themselves. New species will evolve and go extinct. Civilizations we can't imagine will rise and fall on Earth, if Earth survives. Our cities will be dust. Our languages will be forgotten. Every border, every empire, every war, every love story, every achievement we thought mattered, gone. Voyager won't know. It will just keep moving. In 225 million years, one full galactic orbit, Voyager will return to approximately the same region of the Milky Way it's leaving now. The galaxy rotates. Everything in it orbits the center. Voyager, the sun, every star you've ever seen, all of us moving in a vast, slow circle that takes hundreds of millions of years to complete. When Voyager comes back around, the solar system won't be here. We'll have orbited away. Different neighborhood, different stars, different view of the galaxy. Voyager will pass through the space where Earth once was, but will be long gone. It's coming back to an empty house, a neighborhood that moved away, and it will continue, alone, for another orbit, and another, until the galaxy itself disperses or the universe ends. Voyager isn't leaving us. We're leaving it. This is the part that gets me. We built something that will outlast everything we know, every person you've ever heard of, every structure ever built, every word ever written, every song ever sung, all of it temporary, all of it finite. But Voyager, this obsolete machine with 8 track recorders and analog computers, will still exist when our sun is a white dwarf cooling in the dark, when our planet is a memory, if memories still exist. The golden record will still be there, the sounds of Earth, the pictures of humans, the greetings in 55 languages, the diagrams showing where we were, when we were, what we looked like, instructions for a turntable that no one will ever build, evidence of a civilization that briefly existed on a blue planet orbiting a yellow star in a galaxy full of stars just like it. Maybe someone will find it. Maybe, billions of years from now, another species will intercept this silent traveler and wonder what it was. Maybe they'll decode the record and see our faces and hear our voices and know that we were here, that we tried, that we reached out into the darkness with a message of hope and curiosity and said, "We exist, we matter, please remember us." Or maybe no one will ever find it. Maybe Voyager will travel alone forever, the last and only evidence that humanity ever happened. A bottle tossed into an ocean so vast that oceans are irrelevant. Either way, it's still out there, still moving, still carrying us into the future, long after we're gone. That's what Voyager means. Not that we explored the solar system, not that we discovered new worlds or sent back pictures of Jupiter's storms or Saturn's rings. Those things matter, but they're not the point. The point is that we tried, that we looked up at the infinite darkness and built something to go see what was out there, that we thought someone, someday, might want to know we existed, that we believed, despite everything, that reaching out was worth doing. Voyager is the best of us. Not the violence, not the division, not the fear, the curiosity, the hope, the audacity to think that maybe, just maybe, we're not alone. And even if we are, even if the universe is empty and silent and we're the only ones who ever wondered, we still tried. If you enjoyed this journey through space and time, consider subscribing for more explorations like this one. Voyager is still out there, right now, this second, moving at 17 kilometers per second through the dark between stars, carrying everything we were, everything we hoped to be, into a future we'll never see.